לזוכה הוותיק שלנו, אבל זה ותיק ביותר השנה, ג'ון הול, הזוכה במדליה של החברה הגיאולוגית. We are very proud to have John Hall, the winner of the medal of the Geological Society of Israel for significant contribution to the Israeli society in earth sciences. John, please.
Okay, Amos, when I say next, you'll change.
Sure.
Okay. We have been talking about how rapidly things are changing and how we can tie these things down. Well, my last 50 years have been trying to figure out what in hell's out there. So this basically is a view of the last 5 decades of where I've been working, from the mid-Atlantic with the Russians on the first multi-beam mapping of the ridge crest there, to the continental margin off Spain and northern Africa, the IBCM project that produced 70 different charts of various, first the bathymetry and then the geophysical overlays for the Mediterranean as well as the Black Sea. Within JEBCO, the grids produced 20 years ago from Russian spot soundings for the Caspian Sea and for the Persian Gulf. The National Bathymetric Survey, NBS, over Israel, which encompassed some 10 years, and Gidon will continue with that. And then underneath the JEBCO seabed 2030 is the area between Suez and southern Madagascar and over to Sri Lanka, where on the basis of some 700 nautical charts together with cruise tracks, I'm trying to produce the 200-meter grid for wherever data exists for the seabed 2030 that just celebrated the fact that with a great push, we finally succeeded in mapping at a high standard some 20% of the world oceans. And of course, up in the north, there's represented some 13 years of playing around with a hovercraft, which has produced all kinds of data, and our latest map of the Arctic is in Press and Nature. Next, please. Basically, I've been working on infrastructure, and then the first thing was at sea. What do we know about the Eastern Mediterranean? Navigation at that time began with celestial observations, periodically electronic measurements, and it was only some 25 years later that GPS finally came around and we knew pretty much where we were. Bathymetry was from legacy spot soundings, and together with the British Hydrographic Office, I got together all the surveys that have been done by the British following World War II. And as a matter of fact, in the 1860s, when they were opening up commercial markets with the Levant, together with various surveys that were done during the invasion of Lebanon and other times like that, and related to other small surveys. Seismic profiling were in the days where everything was analog and paper records, and ultimately, of course, we're up to 3D seismics, where with software you can run through and just take a look at a cube that's 12.5 meters by 12.5 meters. Satellite altimetry doesn't really apply to our shallow seas here. Satellite-derived bathymetry has been used in some cases, but more and more, basically what you have the charts will work for the JEBCO project. On land, I remember in David Neen's filing cabinet looking in to see what existed for Northern Africa, and basically 50 kilometers in, it was all blank. I engaged in the, first to begin with, the computer at the Hebrew University allowed us to begin computerizing things, digitizing, thanks to the Department of Geography at Hebrew University. And then gradually digitizing in a project of the DTM, the maps of the Survey of Israel with 10-meter contours, and trying to go to grids. And this was all done as PCs were developing, and software to begin with could grid 30 points. And nowadays, we can put in 500,000 points and grid with no problems. I produced a poster with the first image we had from synthetic aperture radar, which began to show that things could be done. And of course, Kitty Bear followed on with that by sequential images before and after earthquakes to see what the ground dislocations were. SAR topography began giving us an idea of what was going on with elevations. The first real 30-meter gridding of 82% of the land masses was done in a week and a half by the shuttle radar topographic mission. This was very painful, very little funding, and surveys here, there, and yon, much manual digitizing, and of course, computation was really difficult. The first DTM that I ran off in the poster, grayscale poster, was 82 hours on a 486. And presentation of results, of course, the reason that I produced so much stuff that was printed was that there was no way of transferring things digitally, and so the best thing to do was to print them. Now I'd like to look at the future. In the past, we got a pretty good idea of what's out there and some indications of what changes are, but I think right now, as a matter of fact, we've got two different systems that give us a much better idea of changes which can occur and what is out there. Next, please. So Earth observation, first optical sensing. There's the new planet system that, funny enough, as of 2 weeks ago, I did not know that it existed. This consists of 150 microsatellites, that is satellites that are less than 100 kilos in weight. And their mantra basically is to be able to map every square meter every day. It's been in operation since 2013, and the resolution of the new satellites, which is sort of an improvement over the Sentinel that were 13 meters, are getting down to resolutions of 3 to 5 meters, although with repetitive monitoring, one can push it to 50 centimeters. There's a short video clip, and Amos, if you will run that, it's 1 minute and a few seconds.
Global change is accelerating, and the world is increasingly interconnected. And satellite imagery has been critical for capturing that change. But the traditional model of satellite imaging isn't keeping pace with the demands of our shifting world. You need to capture change as it happens to make mission-critical decisions in ever-changing contexts. Planet operates the largest commercial constellation of very high-resolution satellites, capturing imagery multiple times a day, providing unprecedented visibility and intelligence. With Planet, you can collect time-sensitive information right when you need it. And with our improved 50-centimeter spatial resolution, you can see even finer details than before. With Planet's rapid revisit capability, you can monitor assets in remote parts of the world, up to 12 times per day. Predict activity, understand events as they're unfolding on the ground, stay ahead of disasters, monitor infrastructure, and track assets. With Planet's new tasking dashboard, you can task what you want, when you want. Request imagery fast and on the fly. Track and modify progress on your own terms. Download the data and make informed decisions. Now, with 6 more SkySats launching soon, you'll be able to capture more, faster, and take decisive action. A world of possibilities awaits you. Act now with Planet, and be ready for the change the world brings.
Next, Amos. Okay. Now, the second part is radar, and primarily synthetic aperture radar, where basically the 7 kilometer per second motion of the satellite gives you a chance to act as if you have a very large antenna and therefore high resolution. Again, we're talking about a constellation of microsatellites In the case of ICE-I, it is two Finnish engineers who got together, wrote a report for a course they were taking, and then formed a company. And it is based upon commercial off-the-shelf or COTS, space-certified components. We're talking about very small components made in very large quantities that are quite cheap and have been certified for operation in space, which is a very hard environment. The next thing is ride-share launching. In other words, now that Falcon 9, for instance, is reusable with their booster, more and more launchings can be done without all the hoopla that went along with NASA's activities. And as a result, up to 30 or 40 of CubeSats and microsatellites can be launched together with whoever's paying for the main launch to put up a much larger satellite. For instance, with the orbit control, now there's a less than 1 kilo square box that takes metallic metal and is able to shoot out ions in various directions in order to maintain orbits. No more thrusters, gases at high pressure, things like that. Another big factor is no matter where the satellite is, can you feed a very high density data transmission either to satellite or ground stations, and then through the network of fiber optic cables that now exist across the oceans, across the continents, to transfer this to the data hub. ICE-I is planning to have the kind of thing where within 30 minutes of reception of data, they can have the data out to somebody who is purchasing it. There's a picture in the corner of what one of these looks like when it's all unwrapped. And again, if we can have the short video clip to entertain you for another 66 seconds. These are all from the same satellite. It's a video. Going to enter half a meter. Open zip line. Okay, next please. Here's an example of two images taken a few minutes apart by two satellites that were launched in the same launch. And in this, you can see in Gothenburg, Sweden, off the port, two ships that are one leaving the port, the other coming into the port. Next.
John, you have 2 minutes to go, please.
Okay, 3D. Sorry, from the same images going over, the same two satellites going over Indonesian islands. Next. Cape Town, coherence, two different images give you an idea what has changed, black, what has not changed, white. Next. Next, this can also be shown as every 28 millimeters, you have a 360-degree change. Here again, there's a spotlight which allows you to concentrate on something as the satellite goes by, getting resolutions down to 25 centimeters, including heights over. Next. Next. This is the airport in Kuwait. While it was building, you can identify all kinds of things in the ground. The same kind of thing for Port Harcourt, Nigeria, with the offloading cranes together with the ships that are at dockside. Next. Next. This is a comparison with the Sentinel 13-meter data as opposed to Port Harcourt. 1 year ago in the Bahamas, the a class 5 hurricane paused for almost a week over the Bahamas. Here you can tell what is water, what is not water, and as a result, there was no communications whatsoever with the islands, but at the same time, pass after pass after pass after pass, you could see the water damage. Next. For ice, of course, for the Finns, this is very important. This is the area between Helsinki in the north and Tallinn in the south. Next. And that's it. I look forward to the kind of things we can get for the acquisition of the software, certainly for the NEEF Center at Hebrew University. I appreciate very much the award of this medal from the Society for the last 50 years of work. Now let's see what you guys can do with all these new tools that we don't have to pay for unless we get something. Thank you.
John, thank you very much for this insightful talk. And with no further ado, we continue.